Unit 3 is our algebra unit, which I know everybody loves to hear that word. Oh, good. Of course, the big thing with algebra is variables. There are actually several different uses of variables, several different types of variables that come out there. A variable is just any symbol that represents a number. We are used to using letters, most commonly, X, Y, N for variables, for missing numbers, but it can be any symbol. When we get in, well, if you guys go on, the next semester of this course would be trigonometry, and in trig, use a lot of Greek symbols, Greek alphabet, for the variables to represent unknown angles. So any symbol can be used. You use the pound sign as a variable if you want to. The uses or applications of variables. We can use variables for rules or definitions. Well, what does this mean? Well, I could have something like x plus y equals y plus x. That's a rule that's stating if I have two numbers and I'm adding them, that it doesn't matter what order I add them. Somebody give me a random number for x. 7, okay? How about for y? 12, perfect. Like 3 people said 12, holy cow. So if I put in 7 for x and 12 for y, what is 7 plus 12? 19. If I put in 12 for y and 7 for x, what's 12 plus 7? 19. That's always going to be true, no matter what numbers we pick for x and y. That's actually called a commutative property for addition. Now, the for addition is very important there because for some other operations, it's not necessarily true. Is it true that x minus y equal y minus x? No, that is not true. If I put in 7 minus 12, that's not equal to 12 minus 7. What's 7 minus 12? Negative 5, there we go. And of course, 12 minus 7, positive 5. Obviously not equal. So there is no commutative property for subtraction. How for multiplication? Does x times y equal y times x? Yeah, if I put in 7 for x and 12 for y, what's 7 times 12? 84, right? How about 12 times 7? 84. So yes, that is true. That's called the commutative property for multiplication.
So what I'm getting at is commutative property is for like equations that move forward, like that add.
Yeah, pretty much. Yeah, because we had mentioned that addition and subtraction were the same operation, one forward, one in reverse. Same with the multiplication and division. Yeah, so the forward operations it applies to. And actually, all the properties of numbers really only apply to the forward operations. Like something called an associative property. Associative property, x plus y plus z. What's that? Oh, there you go. 130. Then we got x plus y plus z again. The parentheses are telling us, of course, to do on this side the x plus y first. On this side, to do the y plus z first. So let's see, we'll stick with x equals 7 and y equals 12. Give me a random number for z. 14, okay. So 7 plus 12 plus 14, what's 7 plus 12? 19, that's 19 plus 14. 33. Over here on the other side, we've got the 12 plus 14 first, what's that? 26, and 7 plus 26, 33. So we get the same answer on each side. So obviously it works for addition. And it would also work for multiplication. X times Y times Z, or X times Y times Z. What is 7 times 12? 84. 84 times 14? 1176. Good. How about over here? What's 12 times 14? 168, and then 7 times 168? 1176. So it works for multiplication. It obviously won't work for subtraction and division. Another one of the rules that we can use our variables to represent. If x equals y and y equals z, what does that tell us about x and z? They have to be equal, yes. Let's say that x is 4.6, y is 4 3/5, and z is 46 tenths. Well, 4.6 is equal to 3.5, or 4. Sorry, 4.6 is equal to 4 3/5, and 4 3/5 is equal to 46 tenths. So the 4.6 must equal 46 tenths. That's all that's saying. If two things are equal to each other, they're equal to. If two things are equal to the same thing, they're equal to each other. You don't need to know these names, by the way. That's called transitive property. If you were to go on to a little bit more of a strict math class, that's something that's used a lot. I don't do proofs in any of the class I teach because I think proofs are kind of useless. Proofs are more of an exercise in logic than they are in math, to be honest. But one of the strategies in proofs is if you're trying to prove two things equal to each other, prove both of them equal to some third thing, therefore they have to be equal to each other. So that's one of our uses of variables, is for rules like that. Another use of our variables is algebraic numbers. In an algebraic number, we're actually using them almost like place values. If you remember our place values for our regular decimal numbers, this first place value is called the ones, right? What's the next one? Tens, careful, hundreds, then the 1,000s, 10,000s, 100,000s, and so on. And those actually are powers of 10. 10 to the power of 0 is 1. 10 to the power of 1 is 10. 10 to the power of 2 is 100. 10 to the power of 3 is 1,000. 10 to the power of 4 is 10,000. And we keep going like that. When I write out a number, we mentioned this way back at the beginning of last fall, like 3,826. That's actually an abbreviation. That's actually 3 thousands, 800s, yep, 2 tens, and 6 ones. But rather than writing out the words, tens, hundreds, and thousands, we could do, oops, helps if I keep my numbers the same, 3 times 10 to the third, using the 10 to the third as the thousands. We saw that a little bit with scientific notation. Plus 8 times 10 squared for hundreds, plus 2 times 10 to the ones is just 10, so I just write tens there. And we often, rather than writing 10 to the power of 0, we just leave no label there, and whenever there's no label put there, That's implied to be ones. When you guys did any basic algebra, polynomials is the term that's used. It's really just an algebraic number is all it is. We had 5x squared, or 5x to the third plus 2x squared plus 7x plus 4. You can see a similarity between writing a number out like this in that expanded form or full form and the algebraic number. The difference is our place values, rather than being powers of 10, are now powers of x. Instead of 10 to the third, it's x to the third. 10 squared becomes x squared. 10 to the 0 is 1, well, x to the 0 is also 1, so that last digit is still just the ones digit in each of those numbers. Everything we do with these algebraic numbers, which we're going to look at probably about half an hour or so, once we see the structure, the similarities between the whole numbers, everything we do with the algebraic numbers is the same as what we would do with whole numbers. Same rules. None of those special rules you were taught when you did pre-algebra or algebra 1. Another use of variables is a formula. And this is probably the most common, most useful application in construction, is you might have something like, P equals 3s. If you're looking at the plates and shoes for a house, it's 3 times the perimeter of the house, 3 times the distance around, is the linear foot of material you need. Well, this formula allows us to take if S is 128 feet, or 128, we can find P by just putting that 128 in for S. What's 3 times 128? 384, good. And of course, there'll be other formulas we run into. We briefly took a look at how to calculate the number of studs for a house. Number of studs equals 12 over the on-center spacing times the length of the wall plus 1 if you're looking at a standard wall. All sorts of formulas like that. Notice again, we don't have to have just a single letter for our variable. NS stands for number of studs, that's a single variable. OC stands for on center or spacing, that's just a single variable. And of course, L is a variable itself. And then we can use variables for something called an unknown. An unknown is probably what you worked with the most if you did any basic algebra. That's things like this: 3x plus 2 equals 17, solve for x. Here the variable has one value. That's one of the differences. These other uses of a variable here, that s can take on different values depending on, of course, sorry, fighting off a sneeze here. Different values, of course, depending on some sort of a real life situation. Up here, in our rules, these could literally take on any values. Positive, negative, decimal, whatever could go in for those. Well, down here, when we're using it as an unknown, that variable already has only one value, well, in most cases. We just don't know what that value is yet, but we're given all the information is there that we can find, we can calculate what that value is. We will spend time doing that, but there are other applications that are more important in construction. So the place we want to start really with Unit 3 is looking at keywords and phrases that indicate operations or indicate how we should convert basically English into math. The two don't always cooperate really well. We start out with simple phrases like a number increased by 6. Now, first we have to decide what are we going to use to represent the number. We can use any letter or other symbols if we want to. For right now, let's just say use n for that unknown number. So how would we symbolize this? How would we write that out in symbols? A number increased by 6. N plus 6. Very good. Increased by indicates 6. Now, there are a lot of other phrases out there that could also indicate n plus 6. We could have a number plus 6, probably the most basic one. Can anybody think of any other examples? Six plus n, that works. 6 plus n or 6 plus a number. The one that often confuses people is this one, 6 more than a number. 6 more than something means 6 has been added to it. Now, not to be confused with 6 is more than a number. How would we write that out in symbols? 6 is greater than or more than a number, using that greater than or less than symbol. Oftentimes, one little word missing or one word being present completely changes that. 6 more than something means 6 is being added to that missing thing. 6 is more than something means it's greater than that thing, being compared to that thing. The one that we always have to throw in here, the sum of a number and 6. Can anybody tell me what the word sum means? Nope. What operation are we using here? Addition. The sum is a result of an addition problem. So whenever you see the word sum, you know that addition is being performed or has been performed. So the sum of a number and 6, once again, would be n plus 6. How about 4 less than a number? Again, we'll use, well, this time let's say use x for the number. How would we write that out? There we go, x minus 4. 4 less than a number indicates 4 is being subtracted from something. It's confusing because the 4 comes first in the statement. You want to put 4 first in your formula. That's why I did put this example out there that way. But 4 less than something is saying 4 is subtracted. Not to be confused with 4 is less than a number. If we said 4 is less than a number, what would that be? Four is less than that, using the less than or greater than symbols, right? Did I show you where those symbols come from? No? Like if I asked you to compare 4 and 9, how do you remember what symbol that is? Well, yeah, the alligator eats the bigger number. Kind of. What it's really asking you to do is it's asking you to compare 4 and 9 on the number line. What side is the 4 on? It's on that side. Notice that's just the arrowhead from the less than symbol, just the arrowhead from that into the number line. What are some other phrases that would indicate x minus 4? I'll give you the obvious one. We might say a number, subtract 4, or a number, take away 4. 4 subtracted from a number. Anybody think of any other phrases? Gotta get those little hamsters turning. Don't worry, at this point in the week, mine's just sitting behind the wheel trying to swat it with its paw. A number reduced by 4. Now, up above we have the sum of a number and 4. Does anybody know the equivalent name for subtraction? There we go, the difference. Now, for addition, it doesn't matter what order we put it. If we had the sum of a number and 4, we could have x plus 4 or 4 plus x. That's that commutative property we mentioned. So it doesn't change things. When it's the difference of a number and 4, the order does matter. The difference of a number and 4 implies x minus 4. If we said the difference of 4 and a number, that would imply 4 minus x. So we do have to go by the order in that case. Of course, difference is just the result of a subtraction problem. Let's say I give you a number repeated 5 times. I tell you to use y as the number. How would you write that? What's that? 5y is one way to write it out. Any other ways you could write it? You could have the 5 and then the y in the parentheses, yep, or both of them in the parentheses. 5 times y. Y times 5 would actually be equivalent because they're multiplication, you can switch the order. But typically we do write it this way just because it's shorter. And whenever we have a number next to a variable, we imply that it's multiplication. Or whenever we have two variables next to each other, if we have x, y like that, it's implied that that's x times y. What are some other phrases that we could have that would indicate 5y or 5 times y? That would be slightly different. That would be y with the little subscript 5. But 5 times the number? Any others? The number times 5 or multiplied by 5, yep. Anybody know the equivalent phrase for multiplication? We have sum for addition, difference for subtraction. Anybody know the term for multiplication? I'll give you the first letter, P. Product, there you go. The product of a number and 5. All those and many more that we could come up with if we sat here and thought long enough would describe 5y, or 5 times a number. If I say we have a number that is split 3 ways, and I tell you to use P for the number, how would we write that out in symbols? P divided by 3, we could use the division symbol like that. P over 3, yes. Perfect. We had mentioned last semester that division and fractions are kind of interchangeable. They're just different ways of writing the same thing. Most of the time in algebra, we actually use that fraction notation just to keep it shorter. What are some other phrases that might indicate P divided by 3? Well, there you go, number divided by 3. 3 goes into a number. So we have sum, difference, product. Anybody know the equivalent word for division? Q is the first letter. Quotient, it's kind of a weird word. And again, just like subtraction, the order matters, so it's the quotient of a number in 3. Would be P divided by 3. If it was 3 in a number, it would be 3 divided by P. It'd be the other way around. So we have all these different phrases that indicate different operations. So in your notes, I'm going to give you a few examples here. I'm just going to have you quickly jot down what mathematical symbols they use. I'm going to have you use N for all of these for the missing numbers. So we'll start out, the first one is a number reduced by 12. The quotient of a number and 9. (14) times a number and 8 more than a number. So a number reduced by 12, what does that represent? N minus 12, good. Quotient of a number 9? Careful. N over 9. Or N divided by 9. 14 times a number? 14N, or 14 times N. And 8 more than a number? 8 plus N, or N plus 8. Where the difficulty comes is when we start combining more than one operation. We might have 5 times a number reduced by 14. What symbols would be used to describe that? What is that describing? What's that? Yeah, multiplication and subtraction. So if we use, let's just use X for a number, how would we write that out? Perfect. 5X minus 14. How about if I have 14 less than 5 times the number? Again, we'll just use X. 14 less than means 14 is being subtracted from something. It's being subtracted from 5X minus 14. So it comes out to the exact same expression. I have 14 taken away from the product of 5 and a number. Once again, 5x minus 14. The product of 5 and a number is the 5x, 14 taken away from, again means 14 is being subtracted from something. 5 times the difference of a number and 14. Be careful with this one. What's that? Remember, difference is subtraction. So you have the right idea. So number in 14 would be x minus 14 instead of 14 minus x. But you have the right idea. X minus 14. But how do we indicate that that has to happen first? Parentheses. Yeah, I knew what you meant. Times 5. All of these other ones, all these other phrases were 5 times a number, 5 times a number. Product of 5 and a number. This one, however, was 5 times the difference. Remember, the difference is the result of a subtraction problem. So this one, it wasn't the number being multiplied by 5, it was the result of that subtraction being multiplied by 5. So we have to make sure that we indicate that the subtraction happens first. Now, most of the time, we wouldn't put the multiplication at the end of the parentheses. We're used to seeing the multiplication in front of the parentheses. But even with the 5 in front of it like that, the parentheses still indicates that x minus 14 is going to happen first. So in your notes, I want you to try to write down what expressions these phrases are describing. $11 more than 6 times a number. We'll use y for the number here. Six times the sum of a number and 11. And 6 times a number increased by 11. Bless you. I'll give you a minute or so to work on those three. Yes. So 11 more, what does that phrase 11 more than mean? Yeah, we're adding 11 to something. It could be 11 plus or plus 11 at the end. 6 times a number? 6x or 6y. Bless you. So if you had 11 plus 6y, that would be fine as well. Bless you again. 6y plus 11 means the same thing. So the next one, 6 times the sum of a number and 11. How do we do there? There you go. It's 6 times the sum, which means we have to make sure the addition is done first. So we put the y plus 11 in parentheses and then the times 6. 6 times the number increased by 11? Well, 6 times the number is 6 increased by 11 is plus 11. Okay. Well, this is one of those things that the only way to really get good at it is repetition. I'm not going to give you a quiz now. I wouldn't do that on your first day back from Christmas. I wouldn't do that to you. I won't give you a quiz. Not today. Next week there'll be one. Don't worry. Start the video. So I'm going to have you, we're going to give you a little bit of work time here in the middle of our class. I'm going to double check, make sure I've got the right pages in your edition of the textbook. This is in the big book. There's some up on the shelf there yet, I believe. It's the big book, the technical math. So one of the other applications we had of variables was in a formula. And we looked at some very basic formulas, like the amount of plates is equal to 3 times the distance around the house, or the perimeter of the house. But as we get to more and more complex formulas, we might have something like D equals 5m minus 3. If we know that m equals 41, to evaluate that, the word evaluate means to put in the values that were given for the variables and figure out what that numerical value is once we've done that. We would put the 41 in for m, and then we have to figure out what this comes out to be. Well, to do that, we need to remember our order of operations. What would we do first here? We do the multiplication. 5 times 4, which is 205. And then 205 minus 3 is 202. Perfect. Excuse me. As soon as I started talking again, the sneeze comes back. Anyway, let's do a quick review of some of our order of operations. So in a problem like this, what would we have to do first? Parentheses. So we're going to start inside that blue box. Inside there, what do we have to do? That's 3 times 5, yes. 3 times 5. There's no other enclosing symbols, no exponents, no powers or roots. So the multiplication is next on our list. What is 3 times 5? 15. So replace the 3 times 5 with 15. Everything else stays exactly the same. So now we're still working inside that parentheses. All that's left is addition and subtraction. So what do we do first? Left to right. Addition and subtraction happen at the same time. That's a common mistake. A lot of people want to add first, but addition and subtraction all happen at the same time, so we're just going to go left to right. So do the 18 minus 15 first, which is 3. So replace the 18 minus 15 with 3. And then we go back and do the 3 plus 2, which is 5. Now we've reduced the parentheses to a single number, which means we can take the parentheses out. But what do we have to remember to put in when we remove the parentheses here? Yeah, the multiplication there. There's a number outside the parentheses with no operation. That is implied to be multiplication. So it's 2 times 5. So now there's no more parentheses, no exponents, so what do we do next? Well, careful. We got to do the multiplication first. 2 times 5, which is 10. So replace the 2 times 5 with 10. Everything else stays the same. Now it's all addition and subtraction, so we will go left to right. So 4 plus 10 is 14. 14 minus 5, is 9. So that comes out to 9. So in something like this, what do we have to do first? 3 squared. There's no enclosing symbol, so we go to exponent. So we've got the power there. What is 3 squared? 9. So replace that with the 9, and the rest of the problem stays exactly the same. What's the next thing we have to do here? There we go. Multiplication and division going left to right. So 2 times 9 would be first, which is 18. What would be next? The division. 51 divided by 17, which is 3. So again, we replace 51 divided by 17 with 3. Everything else stays the same. What's next? Left to right, because it's all addition and subtraction. So 6 plus 18, 24. And then 24 minus 3, 21. And 21 plus 4 is 25. So something like this. What does that line across here mean? It means divide. What else does it mean? It's one of our enclosing symbols. So it means we have to do everything on top separate, everything on bottom separate, then we divide the two results. So let's look at the top first. I'm going to rewrite it over here so we have room to do it. What do we have to do first there? 7 times 8, which is 56. And then 3 times 2, which is 6. And then subtract to get 50. Perfect. So the top of that is 50. On bottom, what do we have to do first? 6 times 7, which is 42. And then the 44 divided by 2 is 22. And then subtract to get 20. So the bottom of that comes out to 20. Our last step, divide. 50 divided by 20 is 2.5. You're correct. So I might ask you to evaluate eight p plus 3m minus d squared for p equals 11, m equals 4, and d equals 3. So the evaluate means we have to replace the letters with the value that's given for them. We've given those values over here. So 8p means 8 times p, and the value we put in for p is going to be 11. So it's 8 times 11. 3m is going to become 3 times 4, and then of course d squared will be 3 squared. Once we have put those values in for the letters, this is just an order of operations problem like the ones we were just doing. What do we have to do first here? Careful. The exponent. 3 squared, which is 9. So replace that with the 9. Everything else stays the same. What's next? Multiplication going left to right. 8 times 11, 88. And then 3 times 4 is 12. Good. Perfect. All that's left is addition and subtraction, so we're going to go left to right. 88 plus 12 is 100. Yes, and minus 9 is 91. Not so bad. I'm gonna have you guys try one. So evaluate f plus d times 3p minus 8m for f equals 11, d equals 4, p equals 7, and m equals 2. Bless you. Bless you again. So our first step is we have to put our values in. So what's f become? 11 plus, what's d going to become? 4. Parentheses, 3p is going to become 3 times 7, and minus 8m will be 8 times 2. So now what's the first thing we have to do when we calculate here? The parentheses. And in there we need to do multiplication. So we're going to go left to right, 3 times 7, 21. Now, if we're doing a lot of these, there are shortcuts you can learn to take. Because the multiplication here is separated by subtraction, we could do both of those multiplications in one step. I'm writing it out the long way here just because I'd rather have you develop those bad habits on your own rather than me showing them to you for one. But if I were doing this, I would do the 3 times 7 and the 8 times 2 in a single step. The only reason I can do that is because they're separated by either subtraction or addition, which means there's nothing that's going to have to be combined between them. But if it were something like 4 times 3 times 7 times 2, I couldn't do the 4 times 3 and the 7 times 2. I have to do them in order, left to right. So anyway, the next step here then is the 8 times 2, which is 16. What's next? 21 minus 16, which is 5. Now what can we do here now that we've done that subtraction? We can remove the parentheses and remember to put in the multiplication, the 4 times. So then the next step is the times 4, which is 4 times 5 is 20. And finally, 11 plus 20, 31. Perfect. I'm going to have you guys try one more. Actually, I'm going to try 2 more, but we'll do this one first. So we're going to evaluate that 8x minus 3d all over 5m plus p. for x equals 7, d equals 2, m equals 4, and p equals 5. Thanks, sir. So as you put the numbers in, what's the top of this going to become? Good, 8 times 7 minus 3 times 2. The bottom's going to become 5 plus 4 plus, or 5 times 4 plus 5. Good. So then on top of 8 times 7 minus 3 times 2, what do we have to do first there? 8 times 7, which is 56, and then 3 times 2, which is 6, so 56 minus 6 is 50. So Colton had that one. On bottom, what do we have to do first? 5 times 4, which is 20, and then 20 plus 5 is 25. So the bottom is 25. And finally, we divide to get 2. Perfect. One last one to try. Actually do 5p minus 3p squared plus 2. We're going to evaluate that for p equals 4. Yeah, I think it is. So let's take a look at this one. We substitute, and there's only one variable, it just appears more than once. So once you put that in, what does this become? What does it look like? Well, 5 times 4 minus 3 times 4 squared, and then just the plus 2. So the first thing we have to do is the 4 squared, which is 16. And then the 5 times 4, 4 times 5, which is 20. And then 3 times 16 is 48. So the 4 minus 28 is a negative 28. I see exactly what you did. You added the 2 first and then subtracted. You got to do subtraction first. Negative 28 plus 2 is negative 26. You could have, because the 5 times 4 and the 3 times 4 squared were separated by subtraction, as long as you did the 4 squared first and then times 3, it wouldn't matter here. It's just pair form. Sometimes that'll catch you. So again, there are cases, once you do enough of these, you start to realize there are cases where you can do both multiplications at once, or you can do one before the other. This is one where I would have probably done just that. I would have done the 5 times 4 is 20, 4 squared is 16, times 3 is 48. I would have done that all at once, because I know I can get away with it because it's separated by the subtraction. Now, one of the reasons that we would do something like this, rather than just writing out this problem here, is because we might want to substitute different numbers in there. We might be asked to evaluate that expression for p equals negative 3. That changes that problem. So this becomes 5 times negative 3 minus 3 times negative 3 squared plus 2. Now, in this last example we ended up with a negative answer. We ended up having to add and subtract with the negatives. Here, we got to do powers and multiplication with the negatives. So the first thing we have to do is still the power, the squared. What is negative 3 squared? If you punch it in your calculator, if you're not careful, it might try to tell you negative 9. That's not the correct answer. There you go. If I punch it in my calculator as negative 3 squared, it's going to say negative 9. But remember, the calculator does strict order of operations. A power happens before a negative. So it is squaring the 3 and then applying the negative. To make your calculator do that correctly, you have to put the negative 3 in parentheses and then do the squared to get the positive 9. Logan's absolutely correct. Negative 3 squared is negative 3 times negative 3. Has to be a positive 9. So now we've got 5 times negative 3 minus 3 times 9 plus 2. Going left to right, we have the 5 times negative 3, which is what? Negative 15. Then we do 3 times 9, which is 27. So we get a little tricky here. Negative 15 minus 27. Negative 42, very good. And then negative 42 plus 2, negative 40, perfect. So the negatives are coming into play here. So one of the things I want to do before we go is to take a quick review of our operations with negatives. So if I have negative 42 plus, or negative 32 plus 47, remember when it's addition, we can use the number line to combine the numbers. And so what that looks like is, here's 0, negative 32 is going to go which direction, left or right? Left is the negative direction, that's negative 32. 47, is it going to go the same direction or the opposite? It's positive, so it goes the opposite direction. Is it longer or shorter? It's longer. It has a larger absolute value, so it's longer. So the picture here tells us that it's, since that's longer, it goes past 0. So our answer is going to be positive. And because the vectors or arrows go the opposite direction, it's going to be the difference between the two numbers. Yes. Difference between 32 and 47, as Gabe said, is 15. So positive 15, or just 15 is that result. So if I have negative 16 plus a negative 28, here's 0. Negative 16 goes which direction? Left. Negative 28 goes left. So they both go the same direction. Again, obviously on the negative side, the result is negative. Since they both go the same direction, we add their absolute values. 16 plus 28 is, careful, 44. Is that what you said? Yeah. Sorry, I thought I heard 54 somewhere. So 44, negative 44 is correct. Let's have 32 plus a negative 63. So again, from 0, the 32 goes what direction? Right. Negative 63 goes left. Longer or shorter? Longer. So that takes us into the other side of 0, telling us the answer is negative. Do we add the values or subtract the values? Subtract, since the vectors go opposite direction, so it'll be a negative 31. Good. So addition is relatively simple. We can use the number line or use a little sketch to combine the values. Subtraction is where it gets a little bit sketchy. If I have a negative 43 minus 28, the easiest way to handle this is change subtraction into addition. Remember, the subtraction operates on the number that comes after it. So the negative 43 doesn't change. Subtracting 28, remember, becomes adding the opposite. So it becomes adding, what's the opposite of 28? Negative 28. So here we have negative 43 plus negative 28. They go the same direction. What's that result going to be? Negative 71. Perfect. If I have 23 minus a negative 52. Now again, subtraction operates on the number that comes after it. So the 23 doesn't change. Minus a negative 52 becomes adding the opposite of negative 52. So the opposite of negative 52 is a positive 52. And yeah, 23 plus 52 is just 75. We might have a negative 37 minus a negative 14. What's the related addition problem? Remember, the negative 37 doesn't change. The subtraction operates on the number after it. So yeah, negative 37 plus 14. So negative 37, 14 goes the other way. What is it? Negative 23. There you go. So we can change the subtraction into addition, and once we've changed it into addition, we can go back to using the number lines again to combine them, or the sketches at least. Multiplication. Six times negative 8. Well, first, is this going to be positive or negative? Negative. A positive times a negative will be negative. 6 times 8 is 48. So that's a negative 48. If I have a negative 7 times 4, first of all, positive, negative. Negative. A negative times a positive is a negative. 7 times 4 is 28. Negative 8 times a negative 3. First of all, positive or negative? Positive, and 8 times 3 is 24. So remember, when we're dealing with multiplication, if they were both negative or obviously both positive, the result was positive. If there's one of each, the result is negative. If we have multiple numbers multiplied together, Negative 5 times negative 2 times negative 4. Now, without calculating this, is this going to be positive or negative? It'll be negative. There's an odd number of negative signs in there. Negative 40, very good. Again, we have to do it left to right. Negative 5 times negative 2 is positive 10 times negative 4 is the negative 40. If I have negative 6 times negative 3 times negative 5 times negative 2, is that going to be positive or negative? Positive. There's an even number of negative signs, so they're going to cancel out. I'll be positive. Going left to right, what's negative 6 times negative 3? Positive 18. Well, we really should do the negative, or the 18 times the negative 5 next, which is negative 90. 18 times 5 is 90. And then 90 times negative 2 will be positive 180. Very good. That's one where you could have done, yeah, the associative property. You could have done the 6 times negative 3, or negative 6 times negative 3, negative 5 times negative 2, and then multiply those together. That would work, yeah. So in the big book, I have you work on two things. Page 325 through 328. I believe it's exercise 12-3, do the odds there. And then I believe it is page 212 through 216, unit exercises. Do 1 through 91, the odds there. That's just a review of the negatives. We work on that for about 10 minutes, I'll let you guys out of here.